And we're back. Hey, I've got. I'm in the process of grading those quizzes. It's not taking me that long, so I should have those quizzes graded by the end of the day today. I'm waiting. Nothing else bad happens. But you should see those quiz grades go in relatively soon. I don't know. I'm in like the first page. The first page is bad. Is it the back page that's bad?
Oh yeah.
Oh really? So that I'm gonna like hit the brakes.
Yeah. You're gonna want to
It's the fourth place. Just right. Okay, so yeah, Carlos was like, there was a bag.
I did that last year, actually.
Did you really?
Yeah, he let me finish it like the next day. I just turned it in.
All right. So, in terms of where we're headed, remember that we've got one more section to do. Today, one day section, Newton's method for approximating zeros. Sounds really fancy, not that difficult. Next week, on Monday, I will give you the review sheet. I'll let you work on it on Monday and Tuesday. We will start to go. I would love to start to go over the test review on Tuesday, but then I'll go over the rest of it on Wednesday. The reason being is next Wednesday is a late start day for the district. So I will not see you guys for the full amount of time. It'll still be a half period, but I want to make sure that we have a good amount of time to go over some test review on Tuesday as well. Oh man, I changed the test up a little bit from the years past. That means I got to change the test review. I got to make a new test review. Most of it will be the same. All right, but anyway, and then you guys will have your test next Thursday and Friday. Yeah, and that test will be the last grade of the third 9 weeks. Okay. That test will definitely be the last grade of the third 9 weeks because the third 9 weeks ends. I'll have my calendar here. I believe on March 10th. Yeah, March 10th is the end of the third 9 weeks, which is not next Friday, but the Friday after of next week. Okay, yeah. Okay. We'll plan it for you. Got that. Okay. And then I'm out for NHS interviews on that Friday. I mean, over here. All right. Okay, so just so you guys know, that's where we're headed. That's where we're at. And then it'll be moving right into the fourth 9 weeks, the last 9 weeks of your school career. As a late student, crazy.
Wow. Why am I sad?
I know, I'm excited.
About what?
All right, so let's talk about this section. This section really, I could have taught you just kind of like L'Hopital's rule. I could have taught you this section a long time ago if I would have liked to. The only thing that we really need is derivatives, right? The only thing that we really need is derivatives. We spent a long time in chapter 4 talking about graphing functions, right? We spent a very long time about talking about how we graph functions and how we use calculus to inform our graph, right? One of our very first things that we've done is solve for zeros, like the zeros of the function, correct? That's like one of the first things that we've ever done, finding a zero. What happens when you cannot easily find a zero? You're kind of just like stuck, right? If you don't have your calculator, right? If you have your calculator, then life's good, right? Now, let me show you something. Now, the book gives this weird, wacky example with this weird function here. I got to change what the notes look like. I'm just going to show you this function here. Okay. It's a cubic function. If I pan out a little bit, you can kind of see it curve in there. But if I had this function and I said, okay, use calculus to graph this without a calculator, the first thing you would want to do is say, well, okay, well, where are the zeros, right? I think the first thing we did was define the domain and range, but then we said, where are the zeros? Well, x to the third plus 4x minus 7. That's not a trinomial like I'm teaching my Algebra 1 students that you could easily factor, right? That doesn't compute right with factoring, because it's, first of all, it's an x cubed, and factors of -7 that add to get to 4 don't work, right? So how do you find the zeros? Well, without technology, it's kind of impossible, right? We could say, and you could do this on your TI-83s as well. You could zoom in and zoom in and zoom in and say, well, where is that point? I could keep zooming in and zooming in and zooming in, but isn't this irrational? Like, it's somewhere between 1.2553 and 1.2554. And it's a little closer to 1.2554 than it is to 1.2553. But I could keep going and going and going and repeating this process infinitely, right? But the nice thing about Desmos is that I can just click on it and see what it is, right? It rounds it even. Like, I think this is funny. It's funny how this turned out. Look, 1.2554 is all the way over there, and it's telling me it's at 1.2554. The reason being is I've zoomed in far enough that I am seeing it more accurately than it's rounding, right? 1.2554 is just rounded to the nearest 4 decimal places, but I can see that it is actually less than 1.2554. It's on the low end, right? So what we have here, what we can do is use what's called Newton's method to solve for those zeros algebraically. And I'm not actually going to find it exactly, okay? I am going to use it to estimate these zeros. See, Newton was around long, long before technology was able to find zeros like these. And actually, the technology that you have in your TI-83 calculators is using this Newton's method. It's actually just doing it very quickly and very accurately, okay? So what is Newton's method actually doing? Well, look at this graph that we have here. Suppose that we know this function has a 0. We don't know where it is, but we know it has one, right? We know this function has a 0. So what we're going to do is we're going to take some point out here. Oops. x1 comma f of x1. And we are going to find a tangent line, right? How do you find the equation of a tangent line? You run the derivative, right? You run the derivative. Now, if I take that tangent line, can I find the 0 of that tangent line a little bit easier? Yeah, because it's just linear, right? In this case, it looks like it's just linear. At that given moment, it's just linear. Okay, well then, can I find the 0 of a linear function pretty easily? Yes, very easily. Okay, so what are we going to do then? Well, we're just going to keep making that point closer and closer and closer and closer until that 0 gets closer and closer and closer to the actual 0. Okay, we're just going to make that point, start reaching that 0 as close as we possibly can. Okay, so what's any plain old function, linear point slope function? Well, y minus y1 is equal to mx minus x1, right? This is y minus y1 is equal to mx minus x1. So what we're going to do is we're going to pick a point. We're going to pick some value along the curve. And we're going to call that x1 comma f of x1, just like we did up here. So that's why you see f of x1 going in for y1, x1 staying as y1. And what does m turn into? F prime at that x value. We are going to pick a numerical value. And that's kind of a difficult part about this problem, or these problems. Where do you start? Where is the beginning moment in saying, oh, I think this is close enough for this thing? We're going to guesstimate where that value is going to occur. And then we can find the slope at that given moment, which will tell us where that's going to run into the axis. Okay, we can find the derivative and then run that x value through the derivative to find the slope at that given moment. Well, what does that x comma y really need to be? What is the coordinate down here of this 0 that we are trying to look for? Isn't that just x comma 0? Doesn't that y value not have any value? So what we can do is say, well, if this y value doesn't have any number associated with it, well, then we're just going to plug that in right to there. We're trying to find the x value of where that occurs. Well, what we can do is say, we'll turn this into x2, the next version of that number. The next version of that number. So we have 0 as our y value, x2 as your x value, because we're going to keep getting closer and closer and closer and closer to it. That x2 is going to turn to x3. That x3 is going to turn into x4. The x4 is going to turn to x5. The x5 is going to turn into x6 until we get a value that's extremely close to the actual 0. We are never, but please understand, we are never actually going to find the 0 because it's an irrational number. You can never find the exact value of that irrational number. So what we're going to do is just do our best to approximate it. Okay. Now, this equation in here, 0 minus f of x1 is equal to f prime of x1 times x2 minus x1. That is just manipulated. Right here, we can just say negative f of x1 is equal to f prime of x1 times x2 minus x1. And then if I divide that over to the other side, and then subtract the x1, or add the x1, excuse me, I can get this equation down here. And that right there is Newton's method for approximating. That, in a nutshell, is Newton's method for approximating zeros. Because I said now, if it's x2 is equal to x1 minus the quotient, well, I could repeat that process for x3. x3 is equal to x2 minus the quotient. And then x4 would be equal to x3 minus the quotient. And x5 would be equal to x4 minus the quotient. What is the quotient? Well, the quotient is the value of f at that number divided by the value of f prime at that number. And remember that that all stems from point-slope form of the derivative, right? Point-slope form with the derivative plugged in for slope. That is Newton's method. That is Newton's method for calculating as close as we possibly can to any zero. So what are we going to do here? Well, I'm going to require you to start at some value where you think it's going to be pretty close. You know, a lot of times it's going to be 1 or 2 or something. You're going to start at some numerical value. That is your x1. That is your x1. So you're going to find x2 by saying x2 is equal to whatever x1 was, whatever we decide our first value to be, maybe 1, maybe 2, maybe 3, whatever it may be, 1 minus f of 1 divided by f prime of 1. Run that number. That's going to give you x2. And then you're going to use that value to find x3. And then you're going to use that value to find x4. And then you use that value to find x5. And then use that value to find x6 until you've gotten close enough. How close is close enough? I think one of the problems says 8 decimal places close enough. That's getting pretty exact, right? Pretty exact for a lot of our purposes. So let's try it here. Starting with x1 is equal to 2, find the third approximation of x to the third, or sorry, not x to the third, x3 to the root of the equation x to the third minus 2x minus 5. I should have graphed that one. That would have been a good example to start with. X to the third minus 2x minus 5. You know, why not? X to the third minus 2x minus 5. X to the third minus 2x minus 5. Oh, I've zoomed so far in. Oh, jeez. Okay. So here's the 0 that we're going to be looking for. And using Desmos, we can see that it's somewhere maybe 2.094 or something like that. That's pretty close, right? But what we're doing is saying without technology, how do we approximate that? Okay, so remember Newton's method says this: x sub n plus 1 is equal to x sub n minus f of xn divided by f prime of xn. F of xn divided by f prime of xn. That's the formula for Newton's method. Okay, so we are saying x1 is 2. x1 is 2. We're going to make a list over here. We're going to find x2 and then eventually find x3. This is a repeating process. It's called an iterative process. There are iterations to it. One answer is going to lead into the next answer, it's going to lead into the next answer, it's going to lead into the next answer. And this process could go on forever if we truly wanted to. Okay, so x2. We know x1. Let's find x2. x2 is equal to x1 minus f of x1 over f prime of x1. You don't need to write that every single time. I'm just showing you that's what we're plugging in. Well, what is x1? What do we choose it to be? 2. So this is going to be 2 minus f of 2 divided by f prime of 2. Well, what have we not found yet? F prime, right? We don't know what f prime is. Well, that's pretty easy to calculate. That's 3x squared minus 2. Cool, there's f prime. A lot of times that's not as easy to find. But that's since it's simply polynomial. Okay, 3x squared minus 2. All right. So that means I'm going to plug in 2 into my original. So 2 to the third minus 2 times 2 minus 5 gives me negative 1. 2 minus negative 1 divided by f prime of 2. Okay, so that's 3 times 2 squared, which is 4, minus 2. 10. Oh, that's 2 plus 1, 10. Right? So 2.1. So x2 is 2.1. So now we know that my 0 is somewhere above 2.1. Right? I'm getting closer by taking 2 to 2.1. Let's find x3. And x3 is x2 minus f of x2 divided by f prime of x2. Okay, so that would be 2.1 minus f of 2.1 divided by f prime of 2.1. So we just got to go back and run those calculations. So we've got 2.1 cubed minus 2 times 2.1 minus 5, 0.061. Divided by f prime of 2.1, which f prime was 3x squared minus 2. 3 times 2.1 squared minus 2, bless you, 11.23. It's interesting that we're going to narrow. Actually, I said it was going to be above 2.1. That's actually not the case. It actually narrowed down. 2.1 minus, and then we've got 0.61 divided by, 0.061, excuse me, 0.061 divided by 11.23. I forgot to finish my parentheses. That's okay. 2.095. 2.095. That is the third approximation. just by running Newton's method 3 times, how close did we actually get? Pretty close, right? Looking at Desmos here, it looks like it's just below 2.095, which makes sense. That's kind of what our calculator told us anyway. If I wanted to get more exact, could I? Yeah, just run 2.095 through Newton's method. And then take whatever you get there and run that through Newton's method. And so on and so forth until you're sufficiently satisfied. We did all that without need of a graph. Oh, hi. Did you need something?
No, I just want to say good morning.
Good morning. How's it going?
Sorry, you didn't stop to see me this morning, so it kind of.
I was grading these guys' quizzes. Sorry. You want to come in and hang out?
Yeah, I want to learn a little bit. If you don't mind.
We're doing a good lesson today. Newton's method for approximating zeros that you can't find easily.
Gosh, that's a Friday night type.
I know, like you guys are gonna get together tonight. Like, so this weird function, right? You can't factor it. You can't do anything algebraically to find a zero.
No, absolutely not.
So you got to use calculus to approximate what that zero is. You know what we can actually do? We can't find this exact because it's going to be irrational, right? What other types of irrational numbers do we have? Well, obviously there's pi, but what types of irrational numbers do we have? Gavin? Exactly. Roots of non-perfect roots, right? Like square roots of like the square root of 7, right? It's going to be an irrational number, right? Or say, for example, the 6th root of 2, right? The 6th root of 2. What is the 6th root of 2? We don't know. We could estimate it, but we don't know for sure, right? So let's find it correct to 8 decimal places. This is a blast for me. This is great. This is so much fun.
I mean, it's bad when you got to print out the notes to make sure you know what's going on.
Oh, I got you. If I don't have these in my hand,
I mean, this isn't
things go
one
bad.
right here.
No, we're high level. We're next level here. Okay, we got 6th root of 2. That's what we want to try to find, right? But we need a function to find the zeros up. We need a function to find the zeros up. So if I've got the 6th root of 2, how am I going to solve here for x? Well, the 6th root, that would be x to the 6th. Just getting the root over to the other side. And then subtract the 2. That's what I want to try to find. You want to create a function to find the zeros up. Okay, so there's our f of x. F of x is equal to x to the 6th minus 2. So what is f prime? What's wrong? Oh, it is? Oh. Here, let me do this. Spot did it. He did it.
It's last thing, I'm gonna stop being a distraction, but
yeah,
it's rattling that just none of my former students are in here.
Does anybody know Mr. Spottis?
I mean, I had one of these students,
Really?
and I had seniors this year. So
That's true. That's true. They're probably all in the other
They just
class.
don't make it.
Right, yeah. If they had you.
It's not setting them up for success. It's rattling.
So what's f prime? Mr. Spottis, what's the derivative of x to the...
I can't tell you.
What's the... Oh.
I'm learning.
Okay, sorry. What's the derivative of x to the 6 minus 2? 6x to the 5th. You remember that rule where you got to bring it down front? All right, so now, what is our, Newton's method says x n plus 1 is equal to x sub n minus f of x n over f prime.
We're finding the volume of cones next period.
Yeah, I appreciate that. Finding the volume of cones. Yeah, is that worse? All right. The problem is are we told a place to start? No. Okay, so you can use your mathematical estimation skills to guesstimate where you think you could start. What's the 6th root of 2 kind of around?
Yes.
The 6th, don't use your calculator. What do you estimate the 6th root of 2 to be? Think about this. What's the 6th root of 1? 1, right? It's got to be a little bit bigger than that, right?
Just start.
Yeah, the 6th root of 1 is 1. Like what? 1 to the, you know. Well, if we at least know that it's going to be a little bit bigger than 1, let's not, why don't we just guess 1? You know, if we know that it's going to be around 1, why don't we just guess 1? Because no matter what you guess, here's the trick about this. No matter what you guess, you're going to be, it'll narrow into the value that you want, just not as quickly as you hope, right? If we guess 2, okay, guess 2. It'll start converging to where you want to guess 20. Guess 20. You're probably going to have to do a lot more iterations of Newton's method until it actually converges to 8 decimal places. Okay? So let's say we believe somewhere to be, we think it's around 1. Okay? So let's say x sub 2 is going to be 1 minus f of 1. Well, what's f of 1? 1 minus 2 is negative 1. Divided by 6 times 1 to the 5th. 6, right? So we have 1 minus a negative 1/6. So 1 plus 1/6. 1 plus 1/6, which gets me 1.16 repeating. 1.16 repeating. So now what is this telling us? Well, it's getting bigger, right? We believe it to be getting bigger. It might go down just like the other one did, but it's getting closer to say 1.16 repeating. Okay, let's find x3. Now here's the bad part about this, is that now we would have to like approximate that too, right? Let's try to keep that number in. Yeah, let's try to keep that number in. We want to do 1.16 repeating minus f of 1.16 repeating divided by f prime of 1.16 repeating. If we want to truly be exact as we can, let's try to be as exact as we can. Let's try to keep that value in. So it's plugged into my calculator right now, right? So I'm going to use the answer button to plug it in. So I've got my answer, which is 1.16 repeating, minus, okay, I've got f of 1.16 repeating. Okay, I'm going to use 2 parentheses here. Answer to the 6th minus 2 divided by 6 times, and I'm going to put a parenthesis here, 6 times my answer to the 5th. I believe this should work out right. Oh, should I put that in parentheses? I feel like I should, just to be safe. Just to be, where are you going? Where are you going? Just to be safe. Insert a parenthesis here, and we'll tack one onto the end. Okay, there we go. Does everybody see what I'm doing here? I'm taking 1.16 repeating minus f of 1.16 repeating divided by f prime of 1.16 repeating, which will get me this, 1.126, approximately 1.126. Actually, you know what? I'm gonna use it correct to 8 decimal places. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so right at that 7. 1, 2, 6, 4, 4, 3, 6, 7. 4, 4, 3, 6, 7. So x3, 1.1264436 How many decimal places matched from x2 to x3? Like this is correct now. We had the ones place and then the here, right? Now I've got correct to 1 decimal place. I want to go until I'm matching for 8 decimal places. He's like, what are you talking about, man? Now, the nice thing here is, guess what? If I go like this, woo, isn't it all plugged in already? What I do? Okay. I want to copy paste, right? Some of you can like go in and like copy paste. I can't do that in this calculator. If you have this calculator, you use second entry and oh, see now it did. Oh, shoot. I got to keep going until it wraps around. Darn it. I deleted it for you guys to see, and now I've lost it all because I don't want to lose that calculation. Oh, so I'm going to have to start over. Really? Oh, no. How long am I going to have to go? There it is. Do you see what I did there? I hit second entry, and it's saying now, take the answer minus the answer, blah, 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 right? But what is it going to use as the answer? Just the line above it right there. It's not going to jump all the way back to here. I'm just using the line above it. So x4 in this case is 1.1224, 9706. Okay. How many decimal places are we the same as now? Okay, so we've added on another decimal place. Let's run that same calculation again. Second entry. Ooh. 1224 62051 or 6205. 1.1224, and then it was 6205. 6205. So how many are we good now? Okay. I believe that we'll need one more. One, 224, 6204. 1224. Oh, we're almost there. Sorry. We run it one more time. What do you think it's going to be? 204? I think so too. Bingo. Look, and in our calculator, it's the exact same thing now, because now it's gotten even more accurate than our calculator. 1.12246204. 1.12246204. And I'm not going to round that because that's going to keep going, right? Once you get to this value that's the same, that's when you stop. So did I do this one? No, I didn't do this one. Oh, no, this is 2x to the 6. That's the other one. So we know that the second root of 6, or sorry, the 6th root of 2, I said that the wrong way. 6th root of 2 is going to be as accurate as we could get there. The 6th root of 2. Look at that. Okay. You know what your calculator is doing? You know what your calculator is programmed to do? This. It's just doing it super fast. Okay? It's just doing it very, very, very fast and spitting out an answer really quickly. Because that's the only way to calculate irrational numbers like that. Treat it like a function and find the derivatives. We got 6, but we could do this in 6 minutes. Okay, cosine x minus x. Or sorry, cosine x is equal to x, right? We want to find when cosine of x is equal to x. Correct to within 6 decimal places. Now, am I finding even a root here? No, I'm finding when cosine equals, like the function cosine equals y equals x, right? Think about the diagonal line running through, and then cosine, the wave. Okay, so I need to get it down to one function. So let's just call this cosine x minus x equals 0, because I'm finding the zeros, right? There's our f. Okay, what would f prime be? What's derivative of cosine? Negative sine minus 1. So really, this is going to be equal to, xn plus 1 is going to be equal to xn minus cosine x minus x over sine x, negative sine x minus 1. That's what we're going to be running it into. Okay, the trick here is you've got to find an x1, right? When in doubt, what did I pick? I picked 1. When in doubt, pick 1. It's going to converge. It'll get there. If you need to use a graphing device to kind of see where you think it's going to turn out to be, like to estimate that first value, go for it. Okay, so this is going to be, and I'll plug this all in here, 1 minus, put this in big in parentheses, cosine 1 minus 1 divided by negative sine of 1 minus 1. 0.750, what am I going to go? 6 decimal places. 750,363. I'm not going to round. 750,363. 750,363. And then I'm just going to repeat that process. But instead of 1, I'm going to use answer, right? I'm going to go back in here, and everywhere where I saw 1, I'm going to replace that with answer. Answer minus cosine answer. Why are you doing that? Nope, I wanted an answer. Okay, second negative. Okay, there we go. Minus answer. Be careful here. This is negative sine answer. I have to leave that minus 1 because that 1 is part of the function, right? I didn't plug in that 1. That was just there. That was just the constant. 739,112. 739,112. Run it again. 739,085. Run it again. 739,085. That make sense? And honestly, that's how your calculators are programmed to solve those types of problems. You are now smarter than your calculator. The calculator may work a little bit more efficiently, but you are smarter.
I don't know about all that.
You said that.